Good morning, class. We are looking at section 3.11 hyperbolic functions. So let's quickly recap what we covered and then we take it from there. So as always, we have a lot of differentiation formulas, class. Okay. And you got to be comfortable with, especially because of the reverse process coming up, the anti-differentiation or integration is called. The linear approximation was discussed, hyperbolic functions, okay, and their definition. Definitions that everybody, I believe, remembers. Cosh x is e to the power of x plus e to the power of minus x divided by 2, and sinh is e to the power of x minus e to the power of minus x over 2. Then we have some definitions such as hyperbolic tangent is sinh over cosh, and so on and so forth. So with that, we have a lot of identities that are similar to trigonometric identities. As an example, sinh negative x is minus sinh x, because if you recall, sine x was an odd function, just as an example. Sine squared plus cosine squared equals 1. That's from trigonometry. Over here, cosh squared minus sinh squared equals 1. Similar to a certain degree. And then we looked at their graphs. The graph comes from the fact that you are combining e to the power of x and e to the power of minus x, okay? And then we looked at some proofs just the way we did in trigonometry, okay? For example, the proof of cosh squared minus sinh squared equals 1 uses the definition of cosh and sinh and results in the answer. We look at more proofs, okay? We continue with more examples, as we did in trigonometry. Okay. Trigonometric function value would be given, and the rest of it you could come up with the same thing for a hyperbolic function can be given, and the rest you can come up with. And finally, we looked at this example where we did the differentiation, and the differentiation results in using the combination of chain rule with hyperbolic functions. So let's look at new stuff now. Okay, class. So this was the last one that was covered, I believe. And this last question was pretty interesting, and it got a little bit involved. In any event, I hope everybody remembers that. Everybody has gone over that, so it should make perfect sense. So just a quick recap on this last one, okay? You are looking at the product of a hyperbolic cosecant and 1 minus natural log of that, okay? So you use the product rule. The derivative of hyperbolic cosecant is put here, and then the parentheses. Then the derivative of the parentheses, okay, because it's a natural, negative sign remains. Because it's a natural log, you flip it over, you times the derivative of that. And then by the product rule times the first piece, then it's a matter of simplification. All right, and we ended up with this answer. Now, let's look at, as we have trigonometric functions and their inverse functions, we have hyperbolic functions and their inverse functions. The sinh, a hyperbolic tangent are 1-to-1, so they have inverse, denoted by sinh inverse and hyperbolic tan inverse. The cosh is not, because if you recall, the cosh looked almost like y equals x squared, shifted up by 1 unit, as far as the rough sketch, so you have it in your mind, which is not 1-to-1, and restriction makes it 1-to-1, and this is the restriction that is given, okay? So the bottom line is trigonometric functions were not 1-to-1, and we made it so by restriction. In this case, we can do the same thing. So when we look at sinh and the inverse function, okay, there is no restriction for cosh. If you look at the cosh, we do the restriction, okay, and therefore the inverse becomes available because it has to be one-to-one, and you can look at the rest of it as well. Okay. So these are various functions, okay, involving hyperbolic functions and their inverse functions, okay. Now, inverse hyperbolic functions, okay, hyperbolic functions are defined in terms of exponential functions. Their inverse can be expressed in terms of what? Logarithmic functions. The hyperbolic functions are differentiable, so are the inverse hyperbolic functions. So if you look at sinh inverse x is natural log of x plus square root of x squared plus 1 and the rest of it. If you look at their derivatives are given. Now, of course, we will look at the proof class. And I look at the proof and maybe you want to try to do one on your own. But just to give you an idea, okay, the sinh was e to the power of x, okay, minus e to the power of minus x over 2. Now it's an exponential function, but the inverse now is a logarithmic, natural log. So it does make sense because they are inverse of each other. So they use their inverse function accordingly. So hyperbolics use exponential and inverse hyperbolic use log. How does that happen? We'll see in a moment. Also, they have, you can come up with the derivatives. We will discuss that also. But as an example, if you recall, the derivative of sine inverse was 1 over square root of 1 minus x squared. So the derivative of sinh inverse would be 1 over 1 plus x squared or x squared plus 1. So what is my point? My point is they're extremely close, okay? And cosh, okay, cosine inverse was the same thing, but it was had a negative at top. In this case, this is not how it works, 1 over square root of x squared minus 1. So there are similarities and there are differences. There's no questions about that. So what I want to do, the first thing is I want to go over the definition and see why is that a natural log and can we show that? And if we can show for one, we can show for all. So let's look at one of them as an example. So let's show that sinh inverse is a natural log of x plus the square root of x squared plus 1. So let's see how we do that. We start, of course, and we remember all these definitions, okay, class? So we start with letting y be sinh inverse of x, and using the definition of the inverse, then sinh y becomes x. Okay, sinh y becomes x. Okay, so this is by definition of inverse functions. Now, sinh y, everybody, we look at this one. Here's the definition of sinh x. So over here, we are going to replace the x with y. So that means e to the power of y minus e to the power of minus y equals 2. So what are we doing? We are using the definition. Okay. Now what do we do? Cross product. I hope everybody can see that. We can think of this over 1. This times this times that. So that is a cross product, everybody. So you have e to the power of y minus e to the power of minus y times 1, and then equals 2x. Now, what we want to do, we are going to bring everything to the same side. So we are going to move the 2x. So that's the first thing we arrive at. We move the 2x, and here's what we have. And remember what we want to solve for. Eventually, y is sinh inverse, and we are going to solve for y. Remember that we are looking for y. To do that, how do we solve this equation for y? Let us multiply both sides by e to the power of y. Because we don't like this one, we want to get rid of it. So when you multiply this one, becomes e to the power of 2y, or e to the power of y squared. This becomes minus 2x e to the power of y, minus this one becomes 1. I hope you see that when you multiply by e to the power of y, e to the power of y by e to the power of negative y results in 1. Don't forget the sign. Now, we treat this as a quadratic equation, quadratic with respect to e to the power of y. In fact, I'm going to rewrite it in this format. And if you have a hard time dealing with it just the way it is, you can let e to the power of y be, let's say, z, and therefore you have z squared minus 2xz minus 1 equal to 0. And you use the quadratic formula. Everybody remembers the quadratic formula class, right? Okay, minus b. Okay, let's discuss that. Okay, so if you go with this, z becomes minus b plus minus the square root of b squared minus 4ac over 2a. Okay, knowing now what is a and what is b. So let's just use a different color. I hope everybody is comfortable with this or with this, it doesn't matter. Knowing that a equals 1, okay, everybody, b equals minus 2x, and c equals negative 1. So we put it into a quadratic formula. Okay, so what do we get? Minus b, that means minus 2x or 2x, plus minus b squared, minus 2x, when you square it, you get positive 4x squared. Okay, minus 4 times a, which is 1, times c, which is negative 1, you get this one. So this is elementary algebra, believe it or not. Okay, now I hope you realize you can take out the factor of 4 from in here, from, if you let's just write it here. So class, we can say under the radical we have a 4 that comes out as a 2. So the top and the bottom, they have a common factor of 2. We drop them. I hope everybody's following that. I hope everybody's okay with that. And so we end up with e to the power of y being this. Okay. So the question is, y is the positive only. I hope you realize why. This has two answers, plus and minus. We keep the plus only. Why not minus? I hope you realize that this expression, square root of x squared plus 1, is larger than x. So if you go with the negative, this whole thing becomes negative. E to the power of y cannot be negative, okay? So y plus only, this is the reason. Understanding the domain and range of exponential functions, okay? So this is e to the power of y. So how do I get to y? I take a natural log of both sides. So if I take the natural log of both sides, that's the end of the proof. So I hope everybody is comfortable with that. Okay. Now this is really involved because it is the higher, echelon of, if you will, algebra. When you do the quadratic equation formula, you should be really having a decent understanding as to what is A, what is B, what is C. This is a page I would go over it at least one more time to be on the safe side, okay? All right. Now let's take a look at differentiation. When we proved the derivative of inverse trigonometric functions, we did the same thing here. Meaning, what is the derivative of sinh inverse x? We let it be y, and we use the fact by definition sinh y equals x. We did the same thing for sine inverse or cosine inverse or tan inverse, something like that we did. So we want to prove the answer is 1 over square root of x squared plus 1. And after we are done, I highly recommend you do another one on your own. Okay. Now, how do we do that? We use implicit differentiation. Sinh y, the derivative of sinh is cosh, okay? So cosh y. and the derivative of y is y prime or dy dx, and x gives you 1. So I hope you remember we did exactly the same thing with the trigonometric functions. So what is dy dx? 1 over cosh y. And you're practically done. All you have to do, figure out what's cosh, and you remember that cosh squared minus sinh squared equals 1. Remember, cosh squared minus sinh squared equals 1. Okay, so what is cosh? You take this one to the other side and you take a root. Okay, so cosh y is equal to the square root of 1 plus sinh squared. So sinh squared y. So what is sinh? Replace it with x. Okay, everybody. This is the proof. Again, I highly recommend you go over the proof of trigonometry, inverse trigonometric functions we did, and see if you can follow that. And we do the same thing here. Okay. Let's look at a couple of simple examples, okay, to get us going with this differentiation. We are interested in finding the sinh inverse of x squared. Please understand, class, that we are going to use the chain rule. So if by any chance, just as an example, and I want to write one of them, if instead of x class, okay, let's say we have, okay, d dx, okay, of sinh inverse of u, okay, then it becomes du over the square root of u squared plus 1, where u by definition is, I don't know, g of x, f of x, whatever you want to call it, okay? So I didn't write the general format, but I'm hoping by now we realize that it is used. Therefore, if we want to look at this guy, we say, okay, this is our function, g of x or u. So when we go with this formula 1 over, instead of x, we're going to put x squared and square it. And then we need du, we need 2x. So when we square that one, becomes x to the power of 4. And then when we write this one times 2x, all we have to do, rewrite this as following, and we are done, everybody. Okay, so I hope everybody is clear as to how we arrive at the answer. Very simple. Bear in mind, this is a function of x. Here's another example. We want to get, again, the derivative of sinh inverse. Doesn't matter what this is. So what is this? This is g of x or u. So we stick with this formula again, 1 over x squared of x squared plus 1. Instead of x, you're going to put tan x. Okay, you're going to put tan x. And you're going to square it plus 1. Okay, and then du, what is the derivative of tan? It's secant squared. So take a look at what happens. So you replace the x with tan x, and because it's a function of x, rather than x itself, you need the derivative, so secant squared x. And now, I hope you remember that this was secant squared. Now, the final answer is absolute value. The reason why, because class, the square root of secant squared x is not secant x. By definition, is an absolute value. Okay, that's the reason.